Okay, ladies and gentlemen, welcome back. It's 10:10, so I'm gonna get the ball rolling here. And I just want to start this class with just a very quick overview of a sample problem or an example of the kinetics. And these are things you've seen before, probably in Gen Chem and then for sure, and then other places. So here's an example of a gas phase reaction at 298 Kelvin and 1 bar pressure, and everything will be constant pressure and temperature. Uh, and the pressure is low. So at this low pressure, we can assume that gases follow the ideal gas equation of state. And some of the information that we're given is the delta G formation for all of these species, as I've shown here in this table. Okay, and these are molar properties. As you can see, it's kilojoules per mole. Okay, kilojoules per mole. So it's a per mole. And so we see here that this is really just so these are these chemical potentials, which is just the free energy per mole for a pure species at the temperature of interest in 1 bar. And so we have this tabulated. And a particular question might be that, let's say we start with A moles of H2 and B moles of CO, okay? And we might be interested in knowing what are the moles that are present for each of the species at equilibrium. And so the usual way to do this is to attack the equilibrium constant and the relationships that we have between, with the given information. And so in this case, we have this information, right? And we also know what we have initially in our system. So we don't know what this is at equilibrium or this at equilibrium, or actually H2 and CO2 at equilibrium, because they won't be A and B. And so we can turn to our fundamental relationship here. Delta G naught of reaction at this temperature is equal to minus RT natural log K equilibrium. Okay, we know how to compute this, and that's just going to equal the differences in the product and reactant chemical potentials, reference state chemical potentials, or equivalently the molar free energies, Gibbs free energies of formation at this at standard conditions. Okay, and so once we know that, we essentially have some indication of what log K equilibrium is. So log K equilibrium at this temperature is going to equal this delta G naught at 298.15 over RT, and we just bring the negative to the other side. And we also know that for ideal gases, K equilibrium is just this product, and so we can write a product as a pi, a capital pi, product over all the species, the partial pressure of I divided by the reference pressure raised to mu sub I, where I haven't used the absolute value of the stoichiometric coefficient, but actually the actual value. So one has to keep in mind the sign. And so we can then just kind of put the reaction over RT. Okay, so in this case, what's known is this guy, the temperature, R and T. So we know everything on that side. And then it's just a matter of knowing what the partial pressures of the species are in the system, okay? And you can take PI to be 1 bar, okay? And so now it's just a matter of formulating what the partial pressures would be, right? And so this is sort of this idea of ice, the ice table that you may have seen. So at equilibrium, so let me just write down H2 gas plus CO2 goes to H2O gas plus CO gas. Okay, so initially we have A moles of H2 and B moles of that in 0, 0. Okay, and then at equilibrium, we'll have some amount of moles of A that react. And since the stoichiometry is the same amount of moles of B will react, and then we'll form X and X moles. Okay, so these are the moles initially, and moles at equilibrium, where we know, or we've said that X amount of A moles is going to react X, and by stoichiometry then, because all of the stoichiometric coefficients have the absolute value of 1 in this case, they're all related simply. And so for every mole of A and B that is consumed, you're going to form a mole of H2O and CO. Okay. And so we know that the partial pressure of any given species is just going to be the mole fraction times the total pressure. Okay. And in this case, we know the total pressure, P total, is 1 bar, because that was given here. Okay. And so we know then that the partial pressure of I is going to equal X sub I, where now X sub I is the mole fraction. And so maybe we can actually say that, oh, well, maybe let me change the variable. So let's say epsilon has reacted. So epsilon moles of A, epsilon moles of B, and we form epsilon moles of H2O, sorry, and epsilon moles of CO. That way we can distinguish the epsilons and the mole fractions. So the mole fractions are little x. Okay. And so to get the mole fractions at equilibrium, and so the X sub I at equilibrium, we just add up all the moles, and then for each species, we divide the number of moles of that species present at equilibrium by the total number of moles. And then the total number of moles is going to be A minus epsilon plus B minus epsilon plus epsilon plus epsilon. That just gives you A plus B. If you can add these moles at equilibrium, we see that the total number of moles is A and B. And because of the stoichiometry, the total number of moles has to be conserved, right? Because for every mole that of reactants that reacts, you get 1 mole of products. And so you can't have any less or any more moles at equilibrium in this special case, okay, for this particular case. So at equilibrium, your total number of moles is A plus B, just as in the initial state, okay? And so the mole fraction of H2 is just going to be A minus epsilon over A plus B. For B, you're going to have B minus epsilon over A plus B. And then for H2O, you have epsilon over A plus B, and the same for CO. So those are the mole fractions. Those are the mole fractions at equilibrium. And the rest is now fairly easy, because you can then say K equilibrium at T, okay, which we just defined as this product here, right, is really just going to be the mole fractions, all of the mole fractions that we have raised to the stoichiometric coefficient. So it's going to be epsilon of H2O raised to the new H2O, epsilon CO raised to the new CO, epsilon, so what is the mole fraction here? So all of these will be over A plus B. This will be over A plus B, because that's the mole fraction of these guys. Okay. And now for the reactants, what do we have? Well, we have A minus epsilon over A plus B, and that's for nu sub A, which is H2. And then we have A minus epsilon over A plus B raised to the nu CO2. So that's your equilibrium constant. Okay. Any questions on that? Okay, so now we know what K equilibrium is because we said that K equilibrium, or the log of K equilibrium, is related to the delta G's of formation. And so there you have it. Okay, and so we can solve this equation for epsilon, because that will tell you then how many moles of each species, reactant species, has reacted and how many moles of the products have been formed. Okay.
I think you put A minus epsilon twice for in the products. I know you know what you're doing, but
I don't know.
so on the right two terms in the product, you have A minus epsilon in the numerator twice. Should be B minus epsilon for one of them.
Oh, sorry. Thank you. You're right.
Pro.
Excellent. Thank you, Sheldon. And so, right, because that's for B. And since all of the stoichiometric coefficients in this case are 1 or minus 1, this can everyone sort of tell what this would turn out to be? So the two epsilons would just give you epsilon squared, and that's coming from this guy and this guy, okay? And then we're going to have something on the bottom in the numerator, which is going to be A minus epsilon 1B squared. Sorry, no. I'm jumping ahead. Times B minus epsilon. Okay, that's right. So we have here K equilibrium of T is equal to epsilon squared over A minus epsilon times B minus epsilon. Okay, this is known, and we want to solve for epsilon. This turns out to be a quadratic equation. Okay, and at this point, I think I'm going to stop and see if you can actually finish the problem off. Let's say A is equal to 1 mole and B is equal to 2 moles. Okay, and let's see what people may get. So any questions on that? So if you figure out K equilibrium, and that K equilibrium turns out to be very, very small, okay, what can you say about epsilon? What do you think epsilon would be? Any comments? So if we say, if you, given all the delta G of formation data, and you find that this is relatively small, let's say it's on the order of 10 to the minus 6. Okay, let's say K equilibrium turns out to be on the order of 10 to the minus 6. So it's some number times 10 to the minus 6. That's what that's what that means, order of 10 to the minus 6. So what can you say about epsilon? And in this case, epsilon, sorry, yeah, go ahead.
It'd be close to infinitesimally small.
Okay, it will be small. That's exactly right. It's going to be small. And so, infinitesimally, well, that I guess that's a subjective matter. But certainly it will be small. That's correct. You are correct. So when you solve this problem, and I encourage you to go and do that just for practice. If you get an epsilon, regardless of how you choose to solve the problem. So if you find that K is small and then say, all right, well, that means epsilon is small. In which case, then you might approximate, right? If k is small, which is 10 to the order 10 to the minus 6, then we can say that a is much, much greater than epsilon, and b is much, much greater than epsilon. So therefore, a minus epsilon we can approximate as a, and b minus epsilon we can approximate as b, because epsilon is very, very small. And so in that case, an approximate solution would be k equilibrium of t is equal to epsilon squared over a times b. Okay, and so this would be an approximate solution because you're approximating that epsilon relative to a and b is small, so we're going to neglect those terms in the numerator that have the epsilon, and we'll just use a and b. In which case, then epsilon squared is easily determined. It's just going to be epsilon will be the square root of a, b, k equilibrium of t. Okay, and we take the positive sign here because epsilon we've let be positive the way we've done this calculation. Okay. You could use the quadratic formula. So, and once you get a result here, epsilon should be small, and what that's something that we have to now judge for ourselves. We have to use perhaps some intuition. Should be small, and definitely smaller than A and B. So it's kind of like a self-check, okay? So once you find this guy, you can do a internally self-consistent check. And if you use the quadratic equation, and this is not that difficult an equation for you to use the quadratic approach to solve it exactly, you should again get an epsilon value that if k equilibrium, as you compute, is on this order of magnitude, which is quite small, epsilon should turn out to be small as well. So either way you choose to solve a problem like this, you should get a small epsilon. Okay, and that epsilon then will tell you how many moles are left at equilibrium in the system. Okay. I just encourage you that if you choose to use an approximate approach rather than directly using the quadratic equation, then please state clearly any assumptions you make. So in this case, you can rationalization in the sense that you would have to write down k equilibrium is really, really small, and be quantitative, meaning that it's on the order of 10 to the minus 6. And so what I'm going to assume is that epsilon will be similarly small. And so I can proceed to neglect epsilon with respect to these other values that I have in the system. Okay. Right? And if you choose the direct approach to quadratic, well, then there's no approximation there. You have an exact solution. Under the assumptions of the problem, of course, and you assumed here that the gases behave ideally. Okay, any questions? All right, I encourage you to finish that problem and see what you get. Let's see. Yeah, I'm not going to tell you the answer, but if you get something that is, small, then you should be, your answer should be on the order of some number times 10 to the minus 3. So, okay, for epsilon. And so I'm going to give you an order of magnitude for the result. And if you want the result, just email me or ask me, and I'll give you the exact value. But, so what I mean by this is that your answer will be some number times 10 to the minus 3. Okay, and that indeed is small. It's a very small amount, okay, compared to the 1 mole and the 2 mole that you started with. All right, enough of that. Any other questions or comments on that? All right, so let's move on to a new topic. So that ends what would be on the exam. Again, everything I said in the email. I also would encourage you to go over Maxwell relations. That was one of the lectures that we used, and that was a way to connect changes in thermodynamic potentials to equations of state. And so that was the power of Maxwell relations. So go back over that as well. I don't think I put that on the my guidance, but that is an important part of this course. So Maxwell relations. Okay, so let's move on to a new topic. Any other questions? Okay. So today I want to start looking at phases. Okay, so I want to look at now, we looked at chemical equilibrium. Okay, now I want to look at phase equilibrium. So phases. Okay, and you've already seen this for H2O pure. You have a phase diagram that kind of looks like this, where you have solid, liquid, and vapor. Okay, and this is something called a triple point. Okay, and the lines represent so these regions that are regions, right? So this is a region, this is a region, and this is a region. Okay, so these regions, they represent single phase regions where you have combinations of pressure and temperature that lead to a single phase. So for instance, if I'm at a point here, so here I have a temperature, T1, and here I have a pressure, P1. Okay, if I specify P1 and T1, I'm in this region where I have only vapor. And likewise, if I picked another combination of pressure and temperature here, I would be in a region where I would only have solid, and same as being here, I would only have liquid. Okay. And of course, I think everyone has seen this idea of the triple point, this very special point where you have all three phases in coexistence. And so when we have coexistence, so at the triple point, you have all three, as you can tell from the phase diagram. And then along these lines, along the lines, you have two-phase equilibrium. Okay, so here you have two phases, two-phase equilibrium. Okay, so there you have equilibrium between two phases. And an example of that, let's say you have some liquid, and here is its vapor. Okay, in the case of water, you would have liquid water in equilibrium with its vapor at a particular combination of temperature and pressure. Okay, so we want to first go and understand something about phase diagrams here. Okay. So the other thing to notice about phase diagrams is something called degrees of freedom. This is an important concept, this thing about degrees of freedom, because remember at the beginning of the class, and we've sort of carried along this idea or this notion that to specify a system macroscopically, without having to resort to any information about the velocities and positions of the particles in the system, you need to specify two independently variable intensive properties. Temperature and pressure are a good example of those two independently variable intensive properties. So they're actually called degrees of freedom because you can vary them, okay? And the phase diagram is very good to see that because I can vary pressure. So if I'm looking at pure water, I can vary pressure and temperature independently, okay? I'm allowed to do that. But there's some demons that arise when we look at this. So if I wanted only a single phase present, i.e. solid or vapor or liquid, as I just discussed, I have freedom to choose pressure and temperature independently, okay? Now, it's obvious from the phase diagram that I can't choose all values of pressure, nor can I choose all values of temperature independent, all values, right? I can choose them independently, but not all values. So for instance, for the solid phase of water, okay, there's a range of pressures and a range of temperatures that I'm confined to if I want pure solid water, ice, okay? Within that range, of pressures and temperatures, I can independently vary temperature and pressure. Okay, so I could, right, starting at this point, just vary the temperature and move to this point. I didn't have to vary the pressure. I can just move along this path at constant pressure. I can change the temperature, which means I varied the temperature independent of pressure, and I am still in the solid phase of ice. Of water. Okay, I'm in the ice phase. Likewise, that same argument applies to the liquid and the vapor phase. Okay. So that's great. I have two independently variable properties that if I want to characterize a pure phase of water, solid, liquid, vapor, I can do so, and everything is fine. The problem arises now, or maybe not a problem, but something that causes one to stop and think is, well, along the two-phase equilibrium lines, okay, I lose some freedom. Because if I want equilibrium between liquid and solid water, okay, I'm constrained to this line. That's the line that gives me equilibrium between ice and water. That's this line. So any point along this line is a combination of pressure and temperature, okay, that if I were to expose my system to that combination of pressure and temperature, I will have solid and liquid in equilibrium. Okay, and only along that line, nowhere else, based on the phase diagram I'm showing here. Likewise, for the solid and vapor and the liquid and vapor lines that I'm not going to highlight just to keep things clear. So if we're moving along this red line, the solid liquid two-phase equilibrium line, you see here that you lose 1 degree of freedom. And by that, what I mean is, I no longer can specify pressure and temperature independently if I want to have two phases in equilibrium. Okay, because let's say I specify, okay, let's say I specify a pressure here. Okay, so that's this pressure. And what do we want to call that? P star. We'll just call that P star. So if I specify that pressure, P star, okay, and I want to have solid liquid in my system, there is only one temperature at which that can happen. I cannot choose temperature independently. And the temperature at which that happens is indicated on the phase diagram by now connecting from this two-phase equilibrium line down to whatever that temperature would be. So once I specify that pressure, P star, wanting to have two-phase equilibrium between solid and liquid, then my temperature T star is defined for me. I can no longer specify T independently. Okay? If at P star, I only wanted solid, then I could specify a range of temperatures independently. Likewise, if at P star I wanted all liquid, I could specify a range of other T stars. Okay, I could specify a range. But if at P star I only wanted both liquid and solid, then I would have one temperature that is defined for me. I have no choice what that temperature will be. Okay? So I lost a degree of freedom. Okay? So when I went to two-phase equilibrium, I lost 1 degree of freedom. I could only specify one intensive variable. Okay? I could have chosen temperature. In this example, I just chose pressure. Okay. Now at the triple point, I want to have 3 phases in equilibrium for water: the solid, the liquid, and the vapor. And in that case, I lose another degree of freedom because the only way I can have 3 phases in equilibrium, coexistence, okay, for water, is at one particular combination of pressure and temperature. I can't choose pressure and temperature randomly and have all 3 phases. The combination of pressure and temperature that leads to 3 phases in equilibrium is 1. That's it. I have no choice. So for 3-phase equilibrium, for the case of water and many fluids that are pure, at a triple point, you only have 0 degrees of freedom. Okay, on Earth and anywhere else, this includes Mars or anywhere in the universe, that triple point of water is a property of the water, and there is no way around it. wherever you go, that temperature at which that happens and the pressure at which that happens is set for you. You have no choice. And that's pretty amazing that it turns out to be that way, right? There is no choice that we have, no degrees of freedom, no freedom to choose that physical real state of a fluid, of matter. That's something that we have to accept. And when one thinks about that, that's pretty amazing. It's really amazing. Okay, so that's the discussion. That's sort of the motivation of what we want to sort of quantify now, or at least apply thermodynamics to see why that is. So phase diagrams, of course, are experimental beasts, right? You can actually plot, you can do the experiment by controlling temperature or pressure or any other variable you want. You can even control magnetic fields, magnetization, electrical fields. You can have phase diagrams that are dependent on any number of independently variable intensive properties of a system. Okay, this we just use pressure and temperature because that's something that we're used to. Okay, but someone who's working with spin systems for looking at storage, right, may be interested in magnetization, and that might be on one of the axes. Or if you're looking at photovoltaics and you're looking at voltage, or gap junction voltages, or something like that, right? So this is a very general concept that exists as in terms of a phase diagram. Okay, so let's sort of start with this idea. Okay. First of all, why do we see these three phases? So any comments, first of all? Okay, so the first thing we have to ask is, well, let's say I have a particular pressure, okay? So at a particular pressure, we can let it be P, okay? And in this case, we can use our phase diagram for water. Let me just rewrite that. Okay, so if I pick this pressure, right? Here's the solid, the liquid, and the vapor. I can move across at constant pressure, right? And if I start here and I move across, what happens is that I'll go through a region where I have all solid, and then I'll hit a point where I have both solid and liquid as I vary temperature, because that's what's varying as we go across. Okay, so let me say I start here. So this is my starting point, and now I'm increase the temperature. So I'll start in a phase that's all solid, and then I'll hit a point where I have both solid and liquid. Then I'll get into a region where I only have liquid. Then I'll get to a point where I have liquid and vapor. And then finally, I'll get into a region where I have only vapor. And so how can we understand this? Why does this happen? Can thermodynamics actually allow us to figure out what's going on? So in this case, we're going to sort of back engineer things. Okay, so this is the observation. Okay, so we have this very grandiose theory of thermodynamics. Okay, and can it actually tell us, or at least qualitatively suggest to us that this is what we should see? Okay, starting at a particular pressure. And this is just an illustrative example. I picked this path because it goes through all three phases. Okay, starting at a particular pressure and keeping that pressure constant. Okay, so let's think about this. What do we know? For a pure fluid, okay, we know that mu as a function of pressure and temperature, okay, is equal to the G over N, okay, where G is your Gibbs free energy. And so this is just G bar. Okay, but in fact, what this is the chemical potential. Okay, so we know that so that mu for this pure fluid is equal to G bar. Okay, and so we know that d mu, total differential of mu, is equal to the total differential of this guy. But we know what dg bar is. That's just d bar dp minus s bar dt. Okay. At constant pressure, since I sort of said, well, let's take a look at a process, or let's moving across the phase diagram at constant pressure, dP is going to be 0. So we get d mu is equal to minus S bar times dt. Okay. And then we can say, all right, well then minus S bar is equal to d mu dt at constant pressure. Okay, so what we have here is that the rate of change of mu versus t, which is really the derivative of mu with respect to t at constant pressure, equal to entropy, the negative of the entropy. That's the slope. So we're looking at phases. We're interested in phase diagrams. And I know that I'm going to have solid, liquid, and vapor as I go through this process from left to right, again in this diagram. Okay, so let's take a look at this. Let's order the entropies, the molar entropies of liquid, gas, and solid. Okay, I think it's not that surprising. No one will disagree that S bar of a gas, the molar entropy of a gas, is much, much greater than the molar entropy of the liquid. Right? Gas has a higher entropy, and this is experimentally, you can see this in tabulated data. The entropy of a gas, just because a gas can occupy more volume at a particular, the same amount of, if you take the same amount, gas will occupy more volume. And we know that higher volume leads to more states in terms of entropy. Remember, that was how we did the Joule-free expansion. In the Joule-free expansion, the thing that really was at the heart of all of this was volume increasing, or essentially the number of sites, because it was a lattice model, but still, the number of sites and the volume increase are highly correlated in that sense. One is a proxy for the other. So in this case, the molar entropy of gas is much, much greater than that of the liquid, and the molar entropy of the liquid is much greater than that of the solid. Okay. What that means then is if you look at the rate of change of the chemical potential, mu, d mu dt at constant pressure, we'll see here that the gas has the highest negative slope, because we see that d mu dt is minus S bar. Okay? That's the equation at the top of the screen. So the rate of change of mu as a function of t, which is the slope, the derivative of mu, which is minus S bar, it's a negative, because we know S is always positive. Entropy is one of these things that has an absolute zero. Remember, perfect crystal, S is 0. And then as you move away from that state, S increases. So entropy then is positive, and so minus a positive thing is negative, so that slope is always going to be negative. So the biggest slope, the most slant, is going to be for the gas phase, and the least slope, or the least slant, will be for the solid phase. Okay, so the gas phase will have a if you were to plot mu versus t, the gas phase might have a slant like this. The solid phase, if you were to plot mu versus t at constant pressure, might have a slope like this, which is not as severe. And then the liquid, of course, is going to have something in between. So we kind of make that a little bit like that. Okay, so that's what these three slopes look like. So now we're going to put them all on one plot and see what we obtain in terms of some insights as to phase diagrams. So any questions on this? Okay. So so again, we have a pure fluid. You can take that, you can let this be water if you wish. Okay, you can let it be any fluid. So here we're going to plot use of T, and on this axis we have T, and of course pressure is constant. Okay. So now what we're going to do is just plot those slope lines qualitatively that we determined here and see what happens. Okay. So we can just put anywhere on this plot our solid line, and let's let that be some color. We'll just let that be. The solid is the least severe in terms of its slope. Okay, so I hope all of these turn out to be okay. And then let's say we have water. And then finally we have our gas. Okay, so this is our vapor. This is our liquid. And this is our solid. And what I'm plotting here are now d mu dt, the slopes. And these are at constant pressure. Okay. And so these lines that I've just drawn correspond to these lines here, and these individual plots, I've just put them all on one plot. Okay. And in this case, we picked a particular pressure, and that's always going to remain constant. Okay, so what happens here, okay, so as we're at low temperature, okay, well, we see that we could actually draw these lines out if you want, right? So I could put this, extend this line all the way out to here, and this line I could extend even further. It would probably go off. Okay, and here's the red line. Okay, and this is absolute zero K, so we really can't go in Kelvin. Okay. What is the guiding principle about mu, which is really G? So if you have a system in equilibrium under conditions of constant temperature and pressure, so in this case, we know pressure is constant as we do anything along the axis and temperature. And once I pick a temperature and I let that temperature be constant, now pressure and temperature are constant in the system. And we know that under those conditions, something is minimized. And that something is what thermodynamic potential at constant temperature and pressure is minimized. I think you only have 4, or is it 5? You have 5 to choose from. Anyone want to hazard a guess?
Internal energy.
Not quite. Okay, so you're on the right track, but it's not internal. So what's special about temperature and pressure, right? That's why I said at temperature and pressure. So once you specify temperature and pressure, which one of those potentials will be minimized?
Would it be delta G because you know it's equal to VdP and S dt?
Okay, so it would be the Gibbs free energy. That's right. It's the Gibbs free energy that is going to be minimized. Okay. And so what that means that for a pure fluid, Gibbs free energy is really just mu. It's the free G per mole. And so what we see here at low temperature, based on this plot, of the 3 lines, the lowest line, right, corresponds to the solid. So at low temperature, we're going to have a solid. Okay, so we follow along this temperature scale. So we start here, okay, we're going to have solid, 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 solid. And then something happens. So we're going to we can start anywhere. We can start at 0 Kelvin and start moving in this direction. We increase the temperature. At low temperatures, starting at 0 Kelvin, we see that the lowest chemical potential, i.e. the lowest G, is for the solid. And so what we have is solid. Okay. So now we keep going. We keep increasing the temperature. We keep increasing the temperature. And what happens is this red line intersects the blue line. Well, we have an intersection here. So what that means is, okay, that the chemical potential of the solid equals the chemical potential of the liquid. Or equivalently, any molecule that's in the solid phase is going to have the same chemical potential as any molecule in the liquid phase. Both phases have the same chemical potential. So what do you think? And so because they have both have the same chemical potential, they both have the same molar Gibbs free energy. So a molecule in the gas, sorry, in the liquid or the solid state at that temperature, at this temperature where you see this intersection between the solid line and then the line for the liquid, you'll have both liquid and solid existing because they both have the same G. We know that a system in equilibrium has to have the minimum G. G is minimized. Well, in this case, you have two phases that have the same G, and there's only one G that's available at that temperature. It's at that intersection point. So what happens here is, anyone want to take a guess what this point is? Or what physical process this corresponds to?
Melting point at that temperature?
Melting point. That's right. This is the melting point at this pressure. Correct. Right? Now, the cool thing that happens is if we keep increasing the temperature, starting at the melting point, this temperature, we keep, now we're going to keep moving to the right. Okay. Now, we see that it's not the solid, that red line that's the lowest in chemical in free energy, but actually it's the liquid. Okay. So what happens is now, because of the difference in the slopes of the two phases, the liquid has become lower in free energy, i.e. lower in chemical potential than the solid. And so now what you're going to have in your system is only liquid. Okay. So as we keep increasing the temperature, right? Here we had solid. Okay. Once we hit this point, okay, we're going to have both phases at that point. But then as we increase the temperature further, now we're going to have liquid. Okay, that's pretty cool. So we follow now the lower line, which is the blue line. Okay, we keep going, we keep going, we keep going. Then we see here, wow, okay, so there's another point of intersection right here, where this liquid mu versus T line intersects with the vapor mu versus T line. Okay, and so this guy, that's going to have a particular special temperature, and that temperature is going to be where now you have both liquid and vapor in existence together. And that temperature is called
Heat of vaporization.
temperature. Yes, that's the temperature at which you have vaporization or boiling. That's correct. And now, as I start here and I increase the temperature, what am I going to have left? What phase?
Just vapor.
Yep, vapor. So you see here that we can actually explain the phase diagram and the progression of what we see at constant pressure as we increase the temperature on this phase diagram. And it all arises from the fact that the Gibbs free energy is minimized in the system at equilibrium. This is a very fundamental concept that we need to keep in mind. And the fact that the variation or the slope of mu versus T is given by the entropies. Okay. And so this is an explanation of why we have phases and what happens at these coexistence points. So at coexistence, that means you have liquid vapor, solid liquid, or solid vapor. Okay, you have both phases in existence in your system at equilibrium. Chemical potentials of molecules in both phases are equal. Okay, so the chemical potential of a molecule in either phase is the same. That's why when you have equilibrium at, let's say liquid vapor equilibrium or solid liquid, so ice and water, I know in high school and in Gen Chem, you were told that, well, molecules can go back and forth between the liquid and the vapor phase, right? You've seen, I know everyone has been taught it this way. Molecules of the liquid go up into the vapor, and then from the vapor, they come back into the liquid. Thermodynamically, this is possible because from a molecule's point of view, the chemical potential of that species, whether it's in the vapor or the liquid, in the solid or the liquid, if you have ice water equilibrium, is the same. And remember when I introduced this idea of chemical potential a few lectures back, I said that if you have a system and a subsystem, right? If at equilibrium, the chemical potentials in that whole system have to be the same. So if your system is this equilibrium system where you have both solid and liquid, ice water, if you have ice water in a bath or a bunch of ice water on the sidewalk, hopefully this winter we'll have some snow, right? You'll have some little bit of region where you have ice and water. For all intents and purposes, you can say, well, that's sort of isolated in itself. And what that means is a molecule in the ice can go into the liquid, and a molecule in the liquid can go into the solid, because to that molecule, there's no difference in chemical potential. And so if I'm a molecule in the liquid and I move into the solid, the total G of the system is not going to be changed because it can't, right? At equilibrium, G is minimized. And the system, in this case, is both liquid and water, right? So if I were a liquid molecule and I went into the solid phase, and if something happened to the chemical potential, if it were to be different, then G would change, and then I would no longer be at equilibrium. But because I am the system, this solid liquid system, and I'm at equilibrium, I should have any molecule be able to go from one phase to the other, and it should not change my G, my being I'm the system, which is liquid and solid. Same applies for liquid and vapor. And so this is at the heart of this thing that we call reversible equilibrium or dynamic equilibrium. Maybe that's something you've heard before. And it is because that system, that two-phase system is your whole system, not just one part, not the liquid, not the vapor, not the solid or the liquid, the whole thing. Both phases taken together are your system. And we know from thermodynamics that for the whole system, G is minimized. The Gibbs free energy is minimized because it's at constant temperature and pressure, okay? And so if you have any movement of a molecule from one phase to the other, it cannot change G at equilibrium. It can't. Otherwise, the system would no longer be at equilibrium. You would have to, right? The system would have to do something so that it would go to its minimum value, okay? So again, at the heart of all of this, chemical potential, and G, right? Gibbs, chemical potential, okay? Fundamental, it's everywhere in science and engineering. Okay, so I went over, but I think this is a very, very important concept, and it brings together a lot of things relevant for Thursday. So I hope it was clear. If not, please ask. I'm going to now end the meeting after if there's any other questions or anything like that. Okay, thanks for your participation. Thanks for catching my errors, and that's always appreciated. And I encourage you to go to the review sessions today, the discussions, and then see you Thursday at 7 p.m.
Thank you. Have a nice